Okay, so thank you very much. Thank you to Felix, and thank you to all the organizer, Claudio, Marco, Patrick. I'm gonna say something about, let's say, perspective on which I'm working pretty much in the last years, which is this one of the stochastic gradient flow approach. That in particular is something very interesting to say, I think, I believe, for the level of, let's say, particle physics, not only also there's many implications in astrophysics and in cosmology in general. Seems to be a framework which is wide enough. And why it's wide enough, I can comment about that later if you're interested. Let's say that this is mainly what I would present here, is something done in collaboration with Matteo Lulli, and then with him, with Torsten Asselmayer Maluga, who is here, and with Roman Pasechnik and Emanuele Zappalà. So first, I want to put a little bit the ground of what I'm talking about, and go back to stochastic quantization. But I want to do it in a way which is eventually a little bit provocative. And I want to start from gravity. And as we know, it's where we understand gravity in terms of symmetries is traced back, let's say, to the Hamiltonian formulation in ADM variable. And if you do that, you can see that there are secondary constraints which are the supermomentum, the super Hamiltonian, that generate the time reparameterization and the space reparameterization. And these are basically the equation of motion. Because, if you combine them, you see immediately that you can find the Einstein equation of motion. So, so this basically is telling us that the Hamiltonian is a constraint, as a superposition of constraints that involve Lagrangian multipliers. And then this tells us that eventually, when we are considering the symmetry and the fate of the symmetry, we have to be particularly careful, because when we are summing and we are considering constraints over these symmetries, we have eventually to take into account the fact that we cannot impose a constraint over them, because this would eventually clash with the idea of summing over all the possible paths. So we cannot sum over the possible path, but then constrain the integration with a certain choice of measure with the constraint to be over the classical path. So this is a problem of quantization. This is a problem, if you want, of choice of the measure, okay, in your path integral. And has to do with the fate of the symmetries themselves. So here we boil down to several possibilities that we have a choice of quantization. So we know that we have a canonical approach to quantization, a path integral approach. Let's say that there is a stochastic approach to quantization as well, which is proven to be equivalent to the others. And if you follow this one, you have, let's say, a new perspective for handling the symmetries, because basically you don't have to follow any more direct prescription. You have not to follow anymore, let's say, certain prescription about and further proposed determinant. And you will have a different way and not anymore even the necessity to deal with the Gribov ambiguities, because you develop this from a different perspective. So in particular, this stochastic quantization approach has been applied to extended systems, to quantum field, in the 80s by Giorgio Parisi and Yon Shu. So what is the idea? The main idea is that we are considering a system which is a complex system that is undergoing a relaxation approach. It's dynamics. This relaxation dynamics is dictated, regulated, governed by an equation which is a Langevin equation, and you have a parameter for that, which is a stochastic stochastic time or thermal time, let's say. It's not a stochastic variable, it's a parameter, but I mean, it's usually accounted for as stochastic time, thermal time. And you write basically the flux in this thermal time of your fields with a drift term, which are the classical equation of motion if they equal to 0. And then I mean, you have a stochastic noise. And the stochastic noise is very much important. Usually, I mean, it's in their first work in which they were applying it to gauge fields. They considered I mean, it's Parisian Vu, they considered an additive and Gaussian noise. But I mean, its choice can be more different. Let's say, I mean, there can be several choices that can be taken into account. And I mean, eventually I will comment about the different of them. So while using this approach, as I was saying, you can obtain the average over histories and the average over dynamic measure in terms of an average over the stochastic noises realization with the measure, of course, that you have to find. Or you can substitute it with the probability function, which is the solution of the Fokker-Planck equation, which is associated to the Langevin equation. And this basically enables to find this probability distribution, which will dictate the dynamics of your system. So in here it comes, I mean, to something which is very subtle, is the way you choose your stochastic calculus. This is extremely important because the different choices of the stochastic calculus will impact even the choice of the measure in your path integral. In particular, this has been studied pretty well, for instance, for the case of gravity by Rumpf. We'll cite his work later on. In particular, I mean, there is the Ito calculus, which has been proven to implement the covariance in the superfield space for the case of gravity. But I mean, that holds also non-linearity, which is relevant eventually for the implications for the collapse model approach, and is also, I mean, non-commutative. But this is, I mean, it's another story that I don't want to touch here. Just want to say that this non-linearity will apply, of course, I mean, with enter when you pass, let's say, from the Langevin equation to the Fokker-Planck equation. And it will be relevant at the end in order to find, at least in Euclidean, the equivalence with the Euclidean path integral measure. So as I was saying, this has been applied to the case of gravity already in the 80s, a few years after the paper by Parisian Vu came out. And let's say that the approach has been developed by Rumpf, as I was saying, for the case of Einstein-Hilbert gravity. And always, I mean, it's within an assumption of additive noise, additive tensorial noise. So, and of course, I mean, it's a supermetric was considered in the drift term, and in particular, I mean, it's the study was involving also the fate of different cases that happen for different choices of the lambda parameter in the supermetric. But what is relevant, I mean, it's here, I write an equation, of course, I mean, it should be complemented, I didn't write, but it should be complemented with the same equation for matter. Of course, I mean, it's when you want to consider a system like that, you have to consider the stochastic evolution of both gravity and matter fields. Otherwise, it wouldn't be consistent, of course. So it came then, I mean, it's to consider with Matteo, I came to consider a slightly different approach, let's say, in which the noise is multiplicative. And the reason why we chose a noise which is multiplicative is because we had in mind the consequences of this at the level of the hydrodynamic limit of the theory. The hydrodynamic limit of the theory is recovered in a simple way. And this will be very evident, let's say, in a couple of slides. But the other reason why we consider that is for the phenomenological implications that choice of noise, which is multiplicative, entails. Also at the level of the universality of the origin of the stochastic noise itself. So indeed, this origin is very much connected at the end of the day to the very way you want to consider, let's say, the interpretation of the stochastic noise and the amplitude of the stochastic noise. And again, if we go back to the Langevin equation, using the property of the Ito calculus, we can then write our Fokker-Planck equation and try to solve it with the proper choice, of course, of a particular measure in the way, I mean, we solve it in a functional way. And you can see that the solution of the stationarized Fokker-Planck equation is extremized, even if you start from Einstein-Hilbert. It's not, I mean, it's not extremized by the Einstein equation, but by the Einstein equation with the cosmological constant, where the cosmological constant now is the square of the amplitude of the stochastic noise. So the stochastic noise is basically acquiring the meaning and the interpretation of an effective cosmological constant, which is like a thermal buff, which is due, as I mean, it will be evident in a second, by basically the degrees of freedom that you have, that are torsional degrees of freedom that are switched on out of equilibrium. So as I was saying, if you want to understand what's happening from the gravity point of view, you have to consider the part, the flow, and the Hamiltonian analysis of the stochastic gradient flow. Because the Hamiltonian analysis of the stochastic gradient flow in these ansatz of multiplicativity is telling you that the shift vector and the lapse function, let's say, part, I mean, of course, they don't behave anymore like a Lagrangian multiplier, but they acquire dynamic in the stochastic thermal time. And you can see that, I mean, the stochastic noise actually disappears from the equation for the shift vector. So but the equation from the shift vector is actually the equation that provides you in the non-relativistic limit with the Navier-Stokes equation. So it's actually the component of the Einstein equation in the Hamiltonian formulation that are connected to the hydrodynamic limit. So in this hydrodynamic limit, the only component, which is a stochastic force and component that remain, will be the derivative of this shift vector, which will provide then a stochastic force added to the system. While the first one is a Langevin equation, basically, for the dynamics of the Laplace function, which is what can derive and can produce generically collapse and relaxation phenomena. So, this, from the point of view, of course, I mean, you see this when you couple to matter. You have to couple to a fluid, okay? You have to couple to matter to see. I mean, this that the generator basically of the space diffeomorphism constraint out of equilibrium, okay, give in a relativistic regime not Navier-Stokes, but Navier-Stokes with a stochastic intermittent force. So this stochastic intermittent force is basically creating a vortices, which is basically changing the topology. And this change of topology, creation of vortices, is basically the way in which you're injecting turbulence in the system. So this also connected with at the level of the perturbation, with the fact that we have to think and we have to add to the system a classical universality of probability distribution, which is different than the Brownian motion. So we have to consider a Kardar-Parisi-Young. I mean, this comes from, for instance, if you consider perturbation around quasi-equilibrium configuration for a centrally symmetric, spherically symmetric metric, or even if you consider FRW, I mean, so now I mean, it's not quoted here, but this is also the case. And in particular, this provide the possibility to look at several contexts in cosmology and astrophysics for a phenomenologically different configuration in which you have non-Gaussian eddies that are involved, and also possible implications at the level of the production of the gravitational waves, if you consider, for instance, the spherically symmetric metric. But this is another story. Now, I mean, I want to go back to the point that pertain, let's say, the out of equilibrium story. So, I mean, I was saying that I define equilibrium as the phase in this thermal time. This thermal time is basically energy scale at which you look your system, you investigate your system. Okay, so this is in a RG flow perspective is the energy at which you're invading, you're investigating, you're magnifying the lenses for to investigate your system. So in the infrared limit, the Langevin equation can be statistically averaged in a way that what you find are the equation of motion. So the drift term is equal to 0. Okay, but out of this infrared equilibrium limit, the system does not fulfill the classical equation of motion, so it's not provided with the symmetries, which are the classical symmetries. So what happened in that limit? Well, for instance, let's take into account a metric which is a de Sitter, anti-de Sitter, and perturb around this solution Einstein-Hilbert action. Okay, and you can see that for if you use this gauge, you can see that the perturbation will provide you with an equation, which is, I mean, it's the one for the perturbation, I mean, for the propagation of the two modes, tensorial two modes, I mean, the spin plus minus 2 of the graviton. But then, I mean, you have also ghost, which we know for gravity in the vacuum does not exist. Indeed, I mean, there is a conformal Killing vector that can be used to gauge out this ghost. But if you are out of equilibrium, this conformal Killing vector is not there anymore. So basically, these degrees of freedom is in the picture if you're out of equilibrium. So this is to say that if you start from a formulation of gravity, which is a first order formulation in which you have that one of the equation of motion is a Cartan equation, when you're out of equilibrium, you have torsion automatically. Because, I mean, you don't close the equation of motion for the same reason. And that's why, I mean, you have to consider, you have to enlarge your connection from a Christoffel connection to a projective connection, which encode also torsion into it. And this way to encode torsion, of course, also include in a general decomposition a bare term, which is a cosmological constant. So now, I mean, it's whenever you consider these out of equilibrium situations, you are also including, let's say, the effect of topology. But this effect can be actually labeled in terms of topological, let's say, invariant classes and numbers, and numbers in particular. If you consider to integrate Chern-Simons, let's say, Pontryagin densities, and then I mean, Chern-Simons topological numbers associated to them. So, so now, I mean, this was, let's say, a big introduction to come to the problem. I mean, to the point now. With the point is what has to do all of this with particle physics eventually. Okay, so the idea is that effect that we can see also in particle physics are effect of topology, I mean, topological phase, okay, or Berry phase, or geometric phase, as you want to say. I mean, it's the same Berry as when you give the seminar as one entire page about the name that can be given to the effect itself, but is a result of the geometric configuration in the manifold of the matter which is interacting. And the idea is that the ground states are by itself a submanifold of the space-time manifold. So ground state are not, are basically the effective and the real physical vacuum that we want to consider, we want to understand. It's the dynamics of which we want to unveil when we consider particle physics. And so in this geometric interpretation, we look then at topology change in order to understand the dynamics and the stability of the state themselves. The idea is to map in a dual sense through knot concordance in a four dimension. And here, I quote, refer to this book by Thorsten for more detail, in order to see how this change of topology by itself it happened. Okay, so I will provide here, we'll try to provide here an intuitive picture of this. Of course, for the details, you can go through the paper, which is on the archive. We have a resubmission from this August. And this is something which is, in a certain sense, very much connected to very well-known, let's say, U1 geometric phase, effects that have been studied for the case, let's say, of U1X mechanism. And basically, I want to give you the picture, which is the intuitive picture, which is the following, which is very easy. So we are considering cases in which, and this is not our thought, this was already suggested by Englert, and Englert by itself, was following a superconductive dual picture of confinement. So the idea is that you have that Wilson loop are sourced by a Toft loop, which are concatenated to them. They source them by Stokes' theorem. Very easy. So where is the equivalence with the superconductive, dual superconductive, let's say, model for confinement? Is that, it's basically this a Toft loop. They're like vortices that are sourcing the expectation value of the Wilson loop. But the expectation value of the Wilson loop is what basically will provide you with the area law, which is the way we explain the fact that we have for the potential, okay, between two quarks, we have a growing behavior in the distance, which is basically the string behavior, which is at the onset of our interpretation in terms of confinement. So this is generated by the change of topology, which are basically fluxes of chromomagnetic at oft circuitation of holonomies that are dual and concatenated to the Wilson loop, which are chromoelectric on the other side. So, and this can be seen both from the point of view of what happened in the dynamics in space-time on the manifold, and what happened at the level of gauge configuration. So we can describe, we can map singularity in one and the other sense, and vortices and singularities in terms of let's say, the center symmetries. So coming back then, to this dynamics. So we are studying then, just to be back, we are studying two coupled stochastic differential equations. One for the metric configurations, for the metric field, and the other one for the gauge field, for the gluon field. Okay, and the point is that, so we are then saying that the geometry matters. It matters from the point of view of the change of topology, but it's in a certain sense what we found is even more dramatic. It matters even for dimensional transmutation and to find the very scale of confinement, which was surprising in a certain sense. And was surprising until Thorsten was showing it on a piece of paper. Does I still remember the day? Just something, it's to come back to a topic, which is the stochastic noise. If you have these ansatz of multiplicative ansatz, it's easier to eventually question yourself about what could be the origin of the stochastic noise and if the stochastic noise itself between different fields could be related. And here we come back to a discussion which is about, let's say, is the origin related to chaos? If this is the origin related to chaos, like, I mean, Barry thinks, like many other people thinks, so you can actually relate the origin of the stochastic noise through, I mean, basically another map that create basically the stochastic noise from the chaotic evolution of the field himself. In this case, what I call their psi and psi prime would be equivalent. But this is something that, I mean, is still a work in progress and we are thinking about, and that would be interesting. Also to connect to experiment as well, observable here. So, yeah, no, that's a very good point. Thank you very much for saying that. So everything that, I mean, I'm showing here, and actually I didn't say something, but it's very important. Thank you for telling that. So Perelman was proving the Poincaré conjecture using the Ricci flow. This is a stochastic version of the Ricci flow. Actually, it is a stochastic version of Ricci flow and, let's say, stochastic gradient flow for the gauge field. So is in the same philosophy, but also with the stochastic noise which is added into the game. So but it's very important what you say because, for instance, Perelman recognized the existence of breather in the dynamic. The breather are actually the degrees of freedom that are responsible for the change of topology, and they are basically degrees of freedom which are the torsional one, which are very important from the point.
The constraint, the power, the reasonable action principle, the constraint, the volume element, be a constant.
Yeah. I mean, it's yes. This is connected to the fate of the volume element, but this, I mean, it's the breather, which, by the way, I mean, it's the story of the breather is connected also to the story of the Turk term, which is a term which usually is added, or if you want another term, which is a way to subtract this breather from the way some people have been studying the Ricci flow applied to certain kind of metric configuration like Schwarzschild, Rainer Nostrom, Kerr solutions, and so on. But this is another story, but maybe I'll leave it for later. Anyway, thank you for the question. I mean, coming back to us, this topology change, as I was saying, is, as I was anticipating already, is the onset of through this change of singularity, I mean, change of topology, which are basically induced by the stochastic fluctuations. Yes. It's thank you. No, it should be enough. Thanks. So then, I mean, coming back to us. So now, what is possible to see is that because of this stochastic gradient flow approach, in this stochastic gradient flow approach, we are basically, I mean, this is the relevant point of view because, I mean, if you see it in terms of representation, to create and destroy a knot, to have a dynamics of the braining, you have, you can see it if you think about holonomies, you have to let holonomies to cross. At a certain point, you have to break the diffeomorphism, which is actually what is happening here. You're breaking the diffeomorphism because you're fluctuating out of the equilibrium configuration that, I mean, I told you I defined the equilibrium configuration to be the one in which the equation of motion holds and the symmetry hold, okay? So, but then, I mean, you do that, and what you find at the end is something surprising, but in the end of the day, is exactly the picture, which is the angular picture, okay? If you want to source the area law, you have to create as many pinches, okay, of chromomagnetic effect of Etoft loop. And if you sum many of them, you recreate the area law. The expectation value of the Wilson loops, of the profile function of the Wilson loops, is actually connected to the linking number in between the loop that you're circulating. So, and this is, I mean, it's a key way to understand the confinement from a point of view which is analytical. Then, I mean, I come to what I think is controversial, okay? Controversial in the sense that, I mean, it's unexpected, completely unexpected, because, I mean, we're thinking already, okay, already something that recreate the area law is strong, but, I mean, it's stronger the fact that, I mean, if you consider the rescaling among the leaf, the rescaling among the leaf is such that the running of the only coupling constant that you have, which is, I mean, it's basically the G Newton, and then, I mean, it's the Planck length, can be understood. I mean, it can be recovered in terms of the change of topology, can be linked to the change of topology through the calculations of the difference of the topology of basically the boundary of the manifold that you're considering. And this is basically the topology of the Briscoe sphere that enter into the game. The inverse of this of the Chern-Simons number of the Briscoe sphere enter inside an exponential and provide a factor which immediately stretch this length from a length which is extremely small to one which is exactly of the order of magnitude of the confinement scale, the Fermi scale. Okay, so we go from the so basically we have a topological way to calculate the RG flow of scales that provide is a change of topology from the topology of the three sphere to the topology of an exotic manifold, which is a Briscoe sphere, which is the easiest, the first non-trivial change of topology. Okay, the first non-trivial change of topology provide rescaling, which is a dimensional transmutation from the Planck length to the scale of confinement. And then, I mean, if this work, then you should always work, okay? Because now we have been just predictive. But if this is true, we should be predictive. Then we should be able to do topological spectroscopy, okay? So we should be able to recover, let's say, mass gap for all the mesons, not only, I mean, for the nucleons, as a sequence of topology changes. And this is work in progress. Of course, I mean, if this is true, if there's something true here, it must, this must be the, okay, so I mean, it's, the outlook, I don't think that, I mean, we need to that, but I mean, again, thank you very much for this chance.